So we're now going to move on to using DirectX with Runtime Compiled C++. And this entails passing a variety of pointers through the system table. If we take a look at our main.cpp code, what we'll see is that we have this data for the device context, the swap chain, and the render target. And we're going to want to grab all of that. So using Alt-click, I can just grab the non-static parts, and then I can put these into our system table. And once again, we're going to use the forward declarations of these to ensure that we don't need to include the header files for these if we're not going to use them. So I'm going to place those forward declarations here. And essentially what this means is that anybody, including the system table, that sees these pointers doesn't actually have to include the definitions of the render target views, or sorry, the declarations of the render target views, the swap chain and device context, etc. They can just ignore them because they're pointers. They know that the compiler knows the size, etc. Okay, so once we've done that, we can then use the we can then ensure that we pass through the values into the system table. So we're going to do that in the same way as we did with our system context. We can basically set, now I'm just going to change some values here. Here we have G underscore. I'm going to remove the G underscore because these are no longer part of the globals. These are actually the members of the this system table object. And in this case, I'm just putting P in front. Some people put an M underscore. I often do. In this case, I'm not. So we can put the device is equal to, no, I have to do this after the initialization actually. So I'm going to place this down here. In fact, in order to keep all of the code together for this, I'm going to move the ImGui, get current context. Right, so now that all of these are initialized, this means that the system table that is visible to Runtime Compiled C++ will be able to capture and see those. The other thing we're going to do is, since we're using the system table a lot, we're going to make it simpler to use. So we're going to create a static reference in our system table to the system table and initialize it with the per module interface system table. This also means that we need to include the header for the per module interface, so I'm going to take that from here and we can place that in our system table. So this does add a slight amount of length to any compile that uses this, but to be honest with you, to use the system table in a runtime compiled file, you need the object interface, therefore you need this. And now we should find that we can use G_p_sys instead of this longer sentence. And again, throughout the code, I could just do a copy replace if I wanted to. And here I'm just doing a very simple replace. Tidy up that little bit of code. And that's slightly simpler there. And here we're using G_system table as this is the actual instantiation of this object. Right, once we've done that, we can actually include Direct3D11. But we don't need, in this case, to include the library. So first of all, we can just include D3D11.h into, Runtime Compiled C++. So I'm just including the Direct3D11 header file, and then I can just use the code as is without including the library. And that's because the D3D devices that we use in the system table, these are all defined as essentially, I can't go to definition. Can I get to, yeah. Okay, well, this is actually a slightly nice to view, but you can see that these functions are all virtual functions, and we can pass through this interface through the system table and to our code without actually linking to the Direct3D library itself. So we can move over some functions. So once again, I'm going to go big. I'm going to move our main.cpp over to the right-hand side. And in this case, we're just going to change the code to have some simple code within our RCCP update. You can see that the code that we can move across easily is these two functions here, the omSetRenderTarget and clearRenderTargetView. I'm going to move those straight over and into our main loop. Now we can't as yet move this present call because we have this call to the ImGui DX11 implementation. And this lives within a set of files that we don't currently have access to. So here, and this device context is no longer g_pd device context, it's now g_p sys p device context. So let's change that. And the same with g_main xp main render target view. That's a pointer there. Clear render target view. And here's the clear color. So now we have this clear color available to us, and we can move the clear color from our code over here to the code that we have. So clear color, where is our clear color? So our clear color is here. It's now we pretty much moved all of our state over. Again, we're doing this as an object, and that clear color being used means that we can now remove this one that we added here. And I've got a mistake here. I've somehow managed to delete here. Device context. Okay, I'm just going to compile that in a standard way. Okay, so I've compiled that file. That seems to work. Make sure I've removed the code from over here, and when I moved it over here. Okay, and then I'm going to try and see whether this can work. Just run that again. Move that over to the right. Okay, so that crashes, and in fact, I'm not following my guide as thoroughly as I should do, tutorial guide. So that crashes because I resized the window. So I'm just going to make that small so you can see what's going on here. So I resize the window and it crashes, and it crashes because one of these pointers is invalidated. In fact, the main render target view has been invalidated, and that's due to the fact that we've got some code in main.cpp, which we just closed, where we create the render target, and that creation of the render target happens if we resize. So what you can see if I go move up here is that there is a there should be a function that when window resizes that we reinitialize the right, here we are within our WinProc. We basically have we capture the WM size, and then we do a clean up the render target followed by a creation of the render target. And because we then don't set this to the system table, that means that this breaks. So what we're going to do is debug. We're going to stop debugging, and we're going to actually make it so that instead of using these g_p device context, we're just going to use the ones from the system table directly. That will ensure that the system table values are the ones that we use all the time. So here we're going to basically pass, instead of init with these two, we're going to init with the ones in the system table. So we no longer need to do that. And then we're going to correct all the other errors. So And let me see as we go through. I believe that's everything. Let's compile that file with Control F7, and that's my binding for compile the single file you're in. Press F7 to build, and then run. And hopefully now, yes, as we resize the window up to the right, it doesn't crash, because now we're using the system table pointers for everything, and therefore when we have a resize and we get into this bit of code and we resize these buffers, we don't have an invalid swap chain in the case of the new function that we're calling in RCPP main loop. So this doesn't give us that much functionality. We want to be able to move a bit more of the DirectX code over. And what you can see from the main.cpp is we have this function. So move back to the main loop. We have this function that we're calling ImGui implement DX11 render draw data. And that function is currently in between several calls. So what we could do is, there's a couple of things we could do. We could add a function to the RCPP main loop called present, and then call present within our Runtime Compiled C++ code. But an alternative is to pass the data about this function through the system table so that we can call this function using Runtime Compiled C++. Now we can't just call this function from Runtime Compiled C++ on its own, because then we would need to include all of the ImGui functions here, the code, the ImGui implementation Win32 and DX11. And for a variety of reasons, that won't work well, because these have their internal state that's not part of the context, that's part of the ImGui, that we can't therefore keep hold of. It would work if we created a library out of them and then included the library. But we're going to show a simpler approach for when you just want to use one or two functions, which is to include the definitions for the functions and then include a function pointer in the system table. So if I go to the declaration for this, we have a fairly simple declaration, and we can create a type def for that you can see the form of it here. So we go to our system table, and instead of, in this case, instead of a forward declaration of the structure, we actually include a type def for this function, and then we can simply put this function into our system table as a function pointer, and we can then use that once we've initialized it over here. So we initialize the context here, and we can initialize this function pointer to that function. And we can then move these lines of code into our main loop. So we don't use the g_system table, as that's part of the main.cpp, but the other way of calling it. So here we have our render draw data, and they're in the present call. And I'm just going to remove this second present call here. So we have a couple of errors in our system table. I'm draw data. Okay, so this is a struct, so we're going to put it in a forward declaration for that. Compile again, and this time things appear to work, and the code is working. And if we go to our runtime compile code, we can then, for example, we can change this by presenting 0, and we see that we go to higher frame rate by removing our present call. And once again, we can do what we did in the very beginning of this, which was we can now add in some state, some data. So we can say here we have present interval equals 1. Once we can line all those variables up. And we haven't added any serialization yet to this particular project. So we're just going to add ImGui input int. and we're going to call it the present interval, and we pass it by pointer, by reference. And then we use that prevent interval down in our actual value here. We compile that out, and then we can change that code on the fly over here. Again, with 2 being half the frame rate of the monitor, 30 frames per second. 1 being the full frame rate, which is a 60 frames per second monitor, 60 Hertz. Okay, so that's the first way that we can move code across for Direct3D. But this uses the fact that the majority of Direct3D calls go through interfaces. These are COM interfaces, and these interfaces are pure virtual or abstract, and therefore you don't need any linkage for them. But if you do need linkage, and just move down, then what we can do is we can use the Runtime Compiler Link library. So if I add that code to my main loop, this will now link with the D3D library. And we'll show that because when we actually do our compilation, we should be able to see the entirety of what it's trying to compile on this compile line here. So here we have it compiling. We can see that some various options. It's compiling to this output, and it's compiling these files that you can see here. These are the include directories being set, sorry. Then it compiles RCP mainloop.cpp, and then several object files that have been previously compiled by a previous iteration of the compile. And what we'll see once we've added this, so our code is still running. So I'm going to save it out. This first compile doesn't know anything about the compiler because it's compiling the code that says there is a library. Sorry, it doesn't know anything about the library because this bit of code is not yet compiled. So this is, I think this compilation is now complete. Just saving out again and recompiling just to double check. Okay, yep, so that has compiled. So now when I save this compile out, we should notice that the compile line should include this as a library. So I'm just looking for that now. And there we are. The D3D11 lib is being added as an input. We do not need to set up where we're getting D3D lib from because it's a system library. If we were using our own libraries, then we would need to do so, and we can do so by the function add library dir, which is a runtime object system function that you can call. And if you click on the link, use the library from the runtime modifiable code, you can see here that there are instructions for how to include various libraries. We have an example of how you would use the runtime object system add library directory with a path to the library that you've got. So once we have the library, there are various functions that we can call as part of main.cpp code. For example, we can move over all of the initialization code for the cleanup D3 device, etc., create render target and create cleanup render target can be moved over into our RCPP main loop. So let's try doing that at runtime. So this is still running. This code is running. We're debugging. I can stop debugging, break all, but I'm not going to. I know we can't move all the code over. Sorry, we can't move all the code over because the code exists in main.cpp. We can add new code, but because we've already got this code in here, I can't keep this running and remove the code from main.cpp, although I can start adding code to the RCPP main loop. So one of the things I can do is I can add the functions we're going to need. So we're going to need these functions, and we're going to need them in our interface. And then they're going to need to be virtual functions. And we're going to need to have them equal 0. Now you notice I've still got my code running over on the right, and that's fine. And I'm going to go into my RCPP main loop. Sorry, let's take right here we have the functions down here. These are the functions. I'm going to copy these functions and move them into my main loop. Sorry, the RCPP main loop.cpp structure. So I can put them into here. Just move them up one level, tab them up one level. And then the instances of g_system table, I'm going to have to replace with g_p sys. So I'm going to do this with a search and replace. So I use replace in files. It's usually the easiest. I'm going to replace in just the current document. Click in here to make sure it is that document. And I'm going to replace this g_system table with g_p sys arrow. So that's g_system table dot, because this is the actual object, and then this is through the pointer. Replace all. And hopefully that's fixed all of these. And okay, so these are virtual headers. Now, this code's still running. And you'll note that these virtuals were added after main loop. And you'll note that main was compiled when it only knew about this one function, virtual function. Now, we can, hopefully, let's see if this will work, save out these, which causes a compile. So you should see this started compiling here. Now there was an error, identifier hwind. So I can actually, now the reason I would need to normally include the definition for hwind available in my RCP main loop. But what I'm going to do is I'm going to use a trick, which is also used by quite a few people. I'm going to pass it as a void star. And if we go to RCP main loop, right, and then try compiling that. And then equals and then save that out again. And it looks like the object swap was complete. So this code now exists in RCP main loop. And the interesting trick was that we were able to add all these virtual functions, although main.cpp didn't know about them. And therefore, you would have thought that this call to main loop would have errors because it's calling into a object which now has these other virtual functions. But because these virtual functions were added after main loop, and because main loop, the pointer to main loop still exists within the virtual function table, these new ones added at the end, oops, don't do that. These new ones that have been added at the end don't interfere with that, and so this still does work. So you can actually add virtual functions to an interface so long as you add them at the end of an interface as you do your runtime compilation, which is a useful trick to know. But now we need to remove the code from main and then call these new functions that we have. So to do that, we're going to have to stop debugging. So now we go back to our main.cpp and we're going to remove the creation and cleanup calls from there. And we're going to move their forward declarations because we're not using these ones. And now instead of calling the create device, cleanup device in our own, we're going to be calling them from the runtime compile class. But we'll notice that the initialization of runtime compile happens afterwards, which means that the object for the RCP main loop object does not exist yet. So what we're going to do instead is we're going to initialize earlier. So by initializing earlier, we can then use this in here. And so you can call this system table followed by the interface that we have, followed by create default device. So I'm going to basically then just pop that in front of the code. The cleanup, again here, cleanup render target, create render target. No more errors. I will then compile that file and then run the code, and amazingly it actually worked. And if I just save that out and look at the output, debug. I didn't attach the debugger, so it's useful to attach the debugger when you don't have any other way of seeing the log. So here I will save out my code, and it compiles the code, and object swap is completed here. So that all appears to be working, and we can change and use Direct3D code. In particular, this Direct3D create device and swap chain function requires the use of this library because it's a simple function that exists in that library. So it's not that useful in this particular example to have the device creation, etc., as part of the main function. But in some cases it is. For instance, when you recreate your device, if you're creating new windows, etc., you might want to have that as part of runtime compiled code. In addition, there are functions for shader generation which you'll want to be able to use in runtime compiled code. And unless you create some system with an interface for that, you could just put that code into your runtime compiled code itself so that you can call all of those Direct3D functions internally within this code. So hopefully this has shown you the basics of how to get this code up and running. If you take a look at the example online, this will also show you more code. For example, in the main loop, we have code for a compiling information widget, which just shows you very simply that there's a certain amount of time being taken in a compile and whether a compile has succeeded or whether a compile has failed. You can create log windows with ImGui, so you can create a log window using ImGui that displays the log from this stdio log system. There are all sorts of things you can do to improve upon this particular example. And if you go to the Runtime Compiled C++ GitHub page, you'll find that there's a wiki which has more information about the various things that you can do, many of which we haven't actually gone into in this tutorial. Error protection is a way to ensure that when there is a crash within your code as you're developing it, that crash is caught and you can then change your code, save your code out, and this new code will be loaded and run instead of the old crashing code, and you can effectively fix this error as you fly. This is slightly difficult with the ImGui code. And the reason for that is ImGui has a series of approaches to ensure that it catches errors in the start and end of various calls, for instance, the beginning of a window and the closing of a window. And runtime protection doesn't quite work with ImGui very well, but I'm looking into extending and adding support for ImGui with runtime protection, and hopefully I'll be able to do that at some point in the future. But it's very good for catching other errors, and for my own avoid game, which I have, we're able to catch errors in almost all of the code that we're using except for the ImGui code when we're doing our development, which is really good for when you accidentally make a mistake with some of your AI code or other code. You can disable runtime compilation if you want to ensure that the end user target doesn't have it on. In the case of our own game, we disable runtime compilation on the fly, and we have a button in developer mode that allows us to toggle that on. There are various other compile and link options that you can set if you want to have different optimization, etc. There's an undo and redo, which enables you to go back to the last compile. This doesn't change any of the source code, but it just reloads the module from the previous compile. And you can change optimization levels. This is very useful when you want to be able to debug something which is in release. You can basically set the runtime compiled optimization level from release to debug, save the file that you want to debug out, and then only that file will be in debug. The rest of the files will be still in release.